Hello friends, now let us move on the lecture number 3, Introduction to the Direct Stiffness Method. Till now we studied the different types of the displacement function as well as different types of the coordinate systems, what is meant by the primary variables, what is meant by the nodes, what is meant by the different types of the elements. And this is the chapter of the 1D elements. So we need to consider the simple bar or the bar element for the study. So let us move for the study of a direct stiffness method. This one we already studied. In this one, this is the my global coordinate system. This is the my global coordinate system. This is global, and this one is the local coordinate system. And the stiffness matrix is F is equal to K into D into K into D. So this is the generalized displacement function. So in the last lecture we have already studied the two types of the displacement function. The first one is the simple stiffness matrix, and the another one is the shape function. So in a shape function we are using, that is the u is equal to n into your q, that is the shape function multiplied by displacement function, force is equal to. Now here the F is equal to K into D, that is K is the stiffness matrix, and this stiffness matrix we need to calculate. So this total chapter is totally consider a formulation of the direct formulation of the stiffness matrix. Now you knows very well, now this spring is not considered into our syllabus, but I have tried to study, or I have considered this spring as the first part of the finite element analysis, because you are very comfortable with the spring, and in that spring you have already studied the stiffness, so that you never be face the difficulty what is meant by the stiffness. Because once we are understanding what is meant by the stiffness, then and only then we could be able to go further for the study of a finite element analysis. You know the spring always obey the Hooke's law. Hence, whenever I am applying the force here, now let us take this the spring 1 and 2. This is the spring. So at this is the node 1. This is the node 1, and this is my node 2. At this node 1, I would be able to apply the force 1, and at the node 2 there is the force 2, F2. Now when I'm considering the node 1, then there is the deformation taking place, so that is the D1 as well as the D2. Now you know that stresses and all that one are the tensors, hence the axes or the directions also written. So here that is the x, here is also x, here is also x. So whenever I am designating the force, I am designating like F1x. So in a subscript I am writing a 1x. 1 is the at node 1, and x is along x-axis. If I'm writing here y, then that is along y-axis, and on the top of this one I use a cap. So this is the local coordinate system. Means I am representing the force in a local coordinate system at a node 1 along the x-axis. So force in a local coordinate system at node 1 along the x-axis. Similar way, force at node 2 in a local coordinate system along x-axis. On the same way, we could see the displacement also. So the displacement also written in the same way, that is the d cap 1x. Here the d cap d2x cap. So this is at the node 2, and we are interested to find out our simple formula, that is the F is equal to K into D. So this is the formula we need to derive. This is the formula we are interested to remove. But when we are looking for the bar, that time bar is to be bar having this one, that is the AE upon L is to be multiplied to this equation. When we are considering the circular bar, then UG upon L. When we are considering the heat conduction, AK upon L. And when we are considering the fluid flow, then AK XX upon L, that is the XX is along the along the tensor. Here we consider the tensors, and x-axis means the along x-axis, xy is different axes. For that one we need to go for the three-dimensional dimensioning system. So this one is we are interested to derive. So let us start. First of all, select the element. First of all, select the element. We are selecting the element, that is the spring. So this is the node 1, this is the node 1, this is the node 2. Here displacement along x at a 1, displacement at 2. So this, first of all, select the displacement function. So when we are selecting the displacement function, we need to find out what type of the deflection taken place. Now this is the spring. So spring is elongated linearly, and there are the two nodes, and there are the two nodes. So since this one is the linear elongation, hence I am considering the linear function. So linear function, that is u is equal to a1 plus a2x. Now this one, this function, we are not taken arbitrary. There are the method to select this shape function, linear function. So this linear function we are selecting with certain rules. What is that rules? The rules are suggesting that generally we are using the Pascal triangle to find out the linear function. But Pascal triangle is not considered into the chapter number 2. That one is considered later on in a chapter number 4 onwards. Hence, here we are not focusing on the Pascal triangle. Instead of that, we only considering that the number of total number of the coefficient A is equal to total number of the DOA associated with the element. Now, what does it mean? Total number of DOA associated with the element. Now, this there are the two nodes, and these two nodes are moving along x-axis. So the displacement DOF is 1, DOF is 1, DOF is 1, DOF is 1, and there are the two nodes. Nodes are 2. So multiplied by number of nodes, that is the 2. So the in a linear function there are the two terms comes. Two terms come. So u is equal to a1, this is the constant, plus a2x, a2x. Now this form we are writing in the matrix form. So this is the linear form, and this linear form writing into the matrix form is very important. So this is the u is keeping outside. So this is my u is the u matrix, that is the force matrix, is equal to now 1 and x. So I am keeping this 1 and x outside. So this is the 1 and this is the x. So 1 and x, and this is the matrix, singular matrix, a1 upon a2, a1 upon a2, a1 upon a2. So 1 x, this is the matrix, and a2, a1 a2 is a singular matrix. So row matrix as well as this one is the column matrix. So we can very easily manipulate this one. Since this one is the 1 by 2, this is the 1 by 2 matrix, 1 by 2 matrix, and this one is the 2 by 1 matrix, 2 by 1 matrix. If I multiplied these two, then I am getting the 1 by 1 matrix. What is that? 1 by 1 matrix means that one row and one column, means only the one term is come in picture. So if I calculate this one, 1 into a1 plus x into a2, so that is the a1 plus a2x, a1 plus a2x. So this is the matrix form. See, this is very important, this is very important. Conversion of this form into a matrix form to derive the any type of the shape function is very important. So first of all, you focus on this one, how to convert into a matrix form. So I am again focusing on this one, that is 1 and x. 1, here the 1 is available, and this is the x is available. So I keep this one is the outside, and this one is the multiplied by 2. So this is the matrix form, this is the matrix form, this is the linear form. So this conversion is done. Then I am trying to find out the values at the various levels. So u is equal to 1 into x, 1 x matrix, a1 upon a2. So if I keep this is the 0 value, means at the 0 there is a value of a d1x, there is a value of d1x. So let us take this spring, this is the spring, so this is my one first node and this is my second node. So when I am considering the u at a 0, then there is a d1x. When I am considering the at the second node, that is u at a l, then that is the d2x. So if I am considering that d1x is equal to a1, d1x is equal to a1. Now how heat 1 is coming, so I have already knowing my formula, u is equal to a1x, sorry, a1 plus a2x, a2x. Now if I put the value of x is equal to 0, if this equal to 0, because u is 0, so this term is cancelled, so this is 0 and only this term is remain, hence d1x is equal to a1. Similarly, by putting the value of l, that is l is equal to x, so d2x, so a2l plus d1x. Now d1x is equal to a1 plus a2l. So this is the value at the l, or we could say that is a2 is equal to a2 is equal to a2 is equal to that is a2 is equal to that is d2x minus d1x upon l, d2x minus d1x upon l. So u is equal to d2x minus d1x upon l into x plus d1x. Why this is? Because u is equal to u, again here u is equal to a1 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 plus a2 a2l. Now this a2 is equal to this value, a2 is equal to this value, okay, multiplied by l means that is x, so this is x plus a1 is equal to d1x. So this is the u is equal to d1 d2 minus d1x upon l into x plus d1x. So again I am converting this one into the matrix form, hence in a matrix form this one, that is the xl, and this one is the x upon l, and d2 xl, d2 multiplied by x upon l, and this is the d1 upon xl. Hence I am converting this is into the matrix form 1 minus xl into xl d1 x d2 x cap. So this cap is suggesting me this is the natural coordinates, sorry, this is the local coordinate system. The cap suggests this is the matrix form into the local coordinate system. So this is my n1 and this is my n2. So this is n1, so this one is suggesting the n1 and this one is suggesting the n2. So n1 into n2 d1x into d2x. So n1x is equal to 1 minus x upon l, and n2 is equal to x hat upon l. So this is called as the shape function, this is called as the shape function. now now let us move to define the stress and strain displacement, or the stress strain relationship. So let us take, since this delta is the deformation, total deformation, so at this point the deformation in this direction, which one is against the x-axis, that's why, and this one is a positive direction, this is the positive direction, so this is negative direction and this one is the positive direction. It means that d2x is positive, d2x is positive and d1x is negative, d1x is negative. So delta is equal to d2x minus d1x, d2x minus d1x, that is the total deformation of difference between the nodal displacement. Hence we know that stress strain relationship is equal to, that is the stress is equal to k into delta. So that is k is the stiffness matrix. Now delta is equal to d2x minus d1x, d2x minus d1x. Hence now we are moving the element stiffness matrix. So f1 is equal to that is minus t, because I have already mentioned that is against the x-axis, in this direction against the x-axis. So this is the t is at the node 1, at the node 1 force applied at the node 1 is minus t, because this is the equation, so this is minus. Why this is minus? Because the force is applying into a opposite to x-axis, that's why opposite to x-axis, hence this is the negative, so this is the my negative. At the node 2, f2 is equal to positive, hence t is equal to minus f1 at the node 1 is equal to k into d2 minus d1x, while into t f2x is equal to k d2x minus d1x. Now because of this negative sign, I am changing this position, hence my f1x is equal to k, this is minus minus plus and this one is minus, so this one is d1x minus d2x, while f2x is equal to k into d2x minus d1x. So this is the change, this here the d1x, here the d2x. Now I am converting these two equations to considering these two equations into the matrix form. So when I am converting this form into the matrix form, so f1x upon f2x is equal to now see here, that is the k multiplied by this is the k1, this is the minus k. So if I am writing this one is to multiplied, so this is the positive k and this is the negative k, so k minus k. Here this one is to be come, this d1 comes here, so that is minus k, and this one is the plus k, because this is the d2, come here. Now to form this matrix form, so k minus k k f1 f2 is equal to d1x d2x, hence my k matrix element stiffness matrix is k minus k k1. Once we are finding the element stiffness matrix for every element, then there is a need of the assemblage. If there are the three nodes, so let us take this is the node 1, node 2, and in between this is the node 3. So node 1, node 2, and node 3. So element 1 and the element 2. So I need to find out the this one is the k1 for the, this is the element 1, or I would say this is the stiffness matrix for the element 1. Similar way I need to calculate the element stiffness matrix for 2, so that once I am getting these two elements, then there is a need of the assembly addition of these two stiffnesses, means what, that is the k1 that is for the element 1 plus that is the k2, element 2. So that is equal to my global, my total stiffness matrix. So this is called as the global stiffness matrix, and that global stiffness matrix, that is equal to k is equal to e to n of all elements. Similar way the forces also added, and then solve the problem so that you get the solutions, and finally, once we are finding the all the matrix in a right this matrix, then apply the boundary condition and solve the problem. Till we are not knowing the boundary condition, that's why we are not focusing on that one. So in this lecture we are doing the study of how to derive the element stiffness matrix for the spring. So this is the very important manipulation. You focus on this area by repeatedly watching the video, and you also focus this matrix form, conversion of a matrix form. Once you are comfortable with this matrix form, then there is no issue for the further studies. Thank you to all.